Welcome to the 18th lecture of this course, Basics of Fluorescence Spectroscopy. On the last class, what we are discussing is TC-SPC setup, and what I showed you is this setup, which is over here, the right side, this setup which I discussed. However, if you look at the actual TC-SPC setup, that actual TC-SPC setup has more component than what I discussed yesterday, right. So, you have here the CFD, you have this delay over here, you have this polarizer over here, and you have this MCA, but I have not discussed all those things. So, to discuss the necessity of the CFD or delay or this polarizer, we need to discuss little more about the different component of this basic TC-SPC setup, right. So, let us start discussing from the laser part. So, what is laser? Laser is a abbreviation of the light amplification by the stimulated emission of radiation. So, for us, right, for us means that for this TC-SPC setup, right, what we need? We need wide variation of the repetition rate. So, here this is my rep rate, sometimes is also called. That means the time delay between the two successive pulses should be varied as per our desire. So, if these are the two successive pulses, if the time delay between these two pulses is Tp, right, second, then the repetition rate is 1 over Tp hertz, right. So, that repetition rate should be varied as per our desire. When I need the less repetition rate or more time interval between the two pulses, when the fluorescence decay is much longer. Suppose the fluorescence decay is originating from here and ended here, then Tp time delay between the two successive pulses is fine. However, consider this fluorescence decay is longer than this, is originating from here. It has to originate when the pump pulse will come, and then it is going like this way, is slower one. What will happen if the repetition rate is again 1 over Tp hertz, then while it is decaying another pulse will come. So, it will again excite the molecule to the excited state and then it will start decaying. So, the decay pattern will be very much distorted because of the presence of this pulse. Now, in this case what I need? I need the repetition rate to be much smaller, so that the time delay between these two successive pulses are much longer, which will be beyond the 5 tau of this fluorescence lifetime. Okay. So, another requirement is infinitely narrow excitation pulse. That is what I said yesterday, right. So, that is what we are discussing, this delta pulse excitation. Delta pulse means the light is present for some time where the width of this line is 0, right. However, our in real life such kind of pulses are not exist. So, we have some time width of the spectra. So, it is like this. So, I have some pulse width over here. Now, question is, if this pulse width is very high, right, if its pulse width is more than this lifetime, let us say the pulse width is something like this. So, light is on for this time. Obviously, I will not be able to measure this decay, right. So, I need the as much as short pulse as possible for this kind of TC-SPC system, right. So, these are my requirement from the point of view of laser. I will show you the point of view of all other different components like CFT, like PMT and all other things. But for the point of view of laser, what my ideal requirements are wide variation of the repetition rate, so that I can tune it, and the infinitely narrow excitation pulse, that is the delta pulse excitation. Right. But in reality, right, we always encountered a limited variation of the repetition rate. So, for a particular laser, the repetition rate is, say for example 1 megahertz. If even you wish to change the repetition rate to 1 kilohertz, it is not possible. So, we are restricted about that, and also the pulse width cannot be generated as a delta pulse, and it depends on the laser medium. Sometime it is nanosecond duration, sometime it is 100 femtosecond duration, and so on and so forth. So, you also have the picosecond laser pulses. So, as you understand that this limited variation of the repetition rate will limit the measuring capability of the maximum longer fluorescence lifetime of the system, right, and for this certain time width of this excitation pulse will limit our measurement of the lifetime. If the lifetime is shorter than the pulse width, then it will be difficult for us to measure that lifetime. So, for us the pulse width should be shorter than the fluorescence lifetime of the sample, right. And also this another important part is here I have written, which tells you that when you have a excitation pulse which is not delta pulse, that means it has some shape. It could be a Gaussian shape, the shape could be like this, shape could be like this, shape could be like this, like whatever the shape, but this particular shape of the excitation pulse, this is in the time axis, right. So, please note that these are in the time. So, light is off here, is on, and then again it is off here. Light is off here, again it is turned on, and it stayed for some time. The shape is like this, and then light is again off, right. So, like that. So, that will eventually going to distort the decay profile. So, in that case I have to do something to get back the original decay, right. That is called the iterative reconvolution process that I am going to discuss. Okay, let us continue with this laser. So, as I said earlier that if your system will undergo a single exponential decay, then for this exponential nature of the decay, the I will be equal to 0 only when the t equal to infinity, but let us consider that I equal to 0.01, that is just 1% of I0, that I believe that this is going to be 0 intensity. Then you can simply calculate t equal to 4.6 into tau. That means roughly 5 times of the tau if you allow this time window. So, this t right here, this t is my time window required to measure the decay, right. So, if I have this 5 times of the tau time window, then I will be able to measure the fluorescence decay, otherwise not. So, that is the part of the repetition rate. So, if the laser repetition rate is R hertz, then the difference between two consecutive pulses will be R inverse second, and when R inverse is greater than 5 tau, then we will be able to measure the lifetime of your sample by this TC-SPC system, right. Now, let me show you that basic principle of this laser, because when I will discuss fluorescence upconversion, this part will be required, right. So, as I said that laser is light amplification by the stimulated emission of radiation, right. So, I have this L, A, S, E, R, that is what it is called laser. So, laser light, right, has some unique properties compared to the conventional light source. Conventional light source means your tungsten lamp, your xenon lamp, your normal fluorescence tube light, CFL, LED bulb, right. Those are kind of a light source, but laser light has some unique properties compared to such kind of conventional light source. What are the property? Let us see. Property number 1, lasers are generally high monochromatic. So, laser lights are monochromatic light. I can also write that same property as narrow spectral width, that is the same thing, right. I can also say write the same property as high temporal coherence, right. These are all the same thing, right. These are all the same thing. It tells me that lasers are monochromatic, right. The second property of this laser is it can produce highly collimated beam. Right. So, it means that the lights which are coming from the laser, they will not going to diverge similarly to the normal light source, conventional light source. I can write the same property as very small focused spot. It can produce. The same property can also be written as high spatial coherence. The third property of the laser is it can produce high power. So, the power of these lasers are much more than the conventional light source. The fourth property is laser sometimes can have wide tuning range. And the fifth property, which actually we are interested for this particular discussion, is that these lasers can produce short pulses. Depending, so we'll going to discuss briefly about this fifth property, because other properties we are not going to discuss here. So, depending on the laser, right, we have different type of laser. We have, obviously you have heard of the ruby laser, right. There's a, you have probably heard of the helium neon laser and so on and so forth. So, depending on the laser, that means the active medium of the laser, it can produce a different type of pulse width. So, the pulse width can start from 10 to the power minus 9 second for some lasers. It can be 10 to the power minus 12 second for some lasers. It could be also 10 to the power minus 14 second for some lasers, right. So, as you can see, when you will going to measure the fluorescence lifetime, where the lifetime is about a nanosecond, then what kind of laser you need? You need such kind of laser which can produce at least picosecond light pulses, right. If not picosecond, let us say 50 into 10 to the power minus 12 second. So, 50 picosecond, 100 picosecond, something like that. If you are interested in much shorter time scale measurement, then you have to go for such kind of light pulses. So, these are the 10 femtosecond light pulses, 10 femtosecond light pulses. Here it is 50 picosecond light pulse. Now, question is that from where the laser got all these properties, right. So, in one word I can tell that one of the important property of the laser is that laser is an optical oscillator. So, laser is an optical oscillator. That means that this electric field of laser will keep on oscillate with constant amplitude, oscillation with constant amplitude and constant frequency for ever. So, here my amplitude is constant and here is my time axis. So, it will keep on oscillate. So, if I go to plus infinity in this side, is minus infinity in that side, then it will keep on oscillate. So, now if I take the Fourier transform of this, right, what you will get? I will get in the frequency domain, this is in the time domain, I will get in the frequency domain, and in the frequency domain you will get a sharp line, right. That means it is just only one value of frequency in this case. So, in this case that plus infinity minus infinity oscillation. So, if I do the Fourier transformation, this is in the time axis. So, I will get in the frequency axis. So, whatever you will get single line of that. That means, if the laser, if this electric field will oscillate forever, then the color means frequency, right, then the color will be a single color. So, you got a monochromatic light, right, I got a monochromatic light. So, here monochromatic light. You see the first property automatically comes in. Now, the question is that why our normal light sources, right, like spectral lamp, why they are not oscillating with constant amplitude and constant frequency forever? Why? The reason is that those, in that case the emission is just nothing but the atomic emission for the spectral lamp. So, the emission is coming from the molecules or atoms present in the spectral lamp, and they had this definite lifetime, and the emission is coming from the excited state species of those atoms. So, the emission is coming as a burst. So, the emission is present for some time and then emission is not there. Then for the next time the emission is coming from the other atoms, right, present in the spectral lamp. So, if I draw this kind of emission of the spectral lamp, what you are going to see is, let us say amplitude is constant like this, phase is constant, time, but it finish over here, that atom stop emitting. The next atom it start emitting, but that electric field is somewhere here and then it is finished. The next one probably will be like this and then finish. Then you have many such kind of atoms, right. In this case, if the duration of this one cycle for one atom, the electric field is sustained for tau, this tau is not infinity in this case. So, if it is sustained by tau, otherwise the amplitude is constant here, right. Then if you do this Fourier transformation, what you will going to see in that frequency domain, it is not a straight line, so it is not just a single vertical line, but it has some width, and that width is proportional almost equal to 1 over tau, right, it is almost equal to 1 over tau. That means, here it is no longer monochromatic, is no longer monochromatic. That means, I have different colors over here, many colors are present. Right? Here this means one color, this means another color, this means another color, this means another color, right. Okay. On the other hand, if I have this system, if I can make it like that way, it will keep on oscillating, right. Then what you will going to get is a transformation from this high bandwidth to very small bandwidth, so monochromaticity. So, I have to do something so that this system will oscillate forever, the system will oscillate forever, and that is done by this light amplification method, right. So, just give you a simple example for that which we have seen in our real life. So, if you look at the pendulum, no? So, this pendulum will oscillate, like this, and its frequency is equal to 1 over 2 pi root over g by d. Okay. If this pendulum is present in a frictionless environment, there is no friction here and there is no air friction, then this pendulum will oscillate with this particular frequency forever, right. Then I will get a perfect oscillator for this. But as you know that because of the friction, the amplitude of this pendulum will going to decrease as a function of time. So, let us consider the amplitude was like this, and then this pendulum is decreasing, decreasing, and ultimately it will going to stop. So, damped oscillation, right. And if this decay I can write as e to the power minus t by tau. So, this is my time axis, right. Then the Fourier transform of this will be something like this. The central frequency will be f0, right, because I have written at f0 over here, and then delta f will be almost equal to 1 over tau. Now, if you want to make a clock out of this pendulum, the ancient clocks, right, earlier days, right, the clocks were made based on this frequency observed in this pendulum, right. So, then this f0 has to be unique, only one value, otherwise this clock will not run, clock will not give you the correct time. So, for this f0 has a particular value, what you have to do? I have to maintain this oscillation, right, as a constant amplitude oscillation forever. Because of this oscillation, this pendulum, there is a friction with the air. So, and for each oscillation, for each time this ball will come from here to here, right, the amplitude will decrease a little bit because of this friction with the air, right. Now, if you stand here and push this pendulum little bit, why you are doing so? You want to overcome the loss, right. If you can do so, then this pendulum will keep on oscillate with this constant amplitude. So, you are giving a some sort of energy which is used to overcome the loss, right. Then this oscillation will be something like this. Because you have overcome the loss. So, if you take the Fourier transform of this oscillation, this will be like this. So, here delta f is much smaller, right, because the decay is much smaller, this almost constant amplitude. So, you will get a unique value of f0 in this case. Here in the other case, the f0 value changes, it consists of different values, it has a delta f width in the frequency, right. So, in laser we do the very similar thing, so that this loss of this optical electric field the loss of this electric field is not that much. So, it means that it sustained for longer time. Right? Now, in the laser we have a different type of method to get a pulse laser. Right? The first one is Q switching. I am not going to describe all this method because this course is not for this. If you take the course on lasers and its application, then probably you will see that how this Q switching or other process actually works to get the ultra short laser pulse. Second is cavity damping. Third is mode locking. So, these are the different methods by which one can get this from a constant amplitude oscillation to a pulse output of the laser. Okay, so with this let us move to our detector, because in this case just look at our this diagram. So, we discussed little bit about this laser and I said our requirement and what is the reality. Now, I am going to discuss this part, detector. So, what is our ideal requirement? The detector must has the constant gain here, constant gain. I will explain what does it mean, and it should have a perfect response time. To explain these two, let me show you the typical detector. Is a photomultiplier tube. As I said earlier that this is based on the photoelectric effect. So, when incoming photon hits the photocathode over here, it ejects one electron, and then this electron is somehow directed to this device which is called the dynodes, and here this electrons is getting multiplied, right. So, from here 1 to 2, 2 to 4, 4 to 8 and so on and so forth, right. So, ultimately in this anode you will get lots of electron coming out of this anode, which can be detected as a current or as a voltage, whatever you want. Now, the question is that if one photon falls over this photocathode, one photon of a particular color. So, here I am talking about one photon, particle nature, color, wave nature, right. So, one photon of a particular color is falling on this photocathode. Then let us consider that I will get 1 0 0 0 0 0 electrons coming out here. What is the guarantee that when the next photon with the same color, right, next photon of the same color will fall on this cathode, exactly this number of electron will be ejected, right? There is no guarantee. If it is so, I call this as a constant gain. Every time one photon falls of the same color, every time 1 lakh electrons is ejected from this anode, but there is no guarantee like that. That means the detector will not going to operate as with a constant gain, it has a variable gain. So, in this case I have sometime 95,000 electrons coming out, sometime 1 lakh 5,000 are coming out and so on, right. That is a problem. Why? I will tell you later. Another thing, the detector must have a perfect response time. What I wanted to say is that, say at time t equal to t0, the photon falls on this photocathode. what to write here, T equal to T0 photon falls to the photocathode. Obviously, from here to here it will take time, because none of the process is instantaneous, right. It will take some time. Let us say the time taken to from this photocathode to this anode, ejection of this bunch of electrons, it is, let us say, the T t, that means the transit time. So, conversion time from photon to bunch of electrons, let us say I call this as transit time Tt. So, when this electron pulse will come out of this detector, so the electron pulse will come out of the detector at time t equal to T0 plus Tt. Okay. So, we will finish here and we will continue our discussion on the next lecture. Thank you.